Standard intuition regarding AI memory is simple. A bigger context window means a model that remembers more. More room, more recall. Empirical data proves that intuition false. In a controlled study, researchers tested a model's ability to extract a single specific answer from a prompt packed with 20 different documents. This curve maps retrieval success by location. With the target at the top, the model succeeded 75.8% of the time. Buried in the middle, it dropped to 53.8%, worse than scoring 56.1% with no documents at all. Overloading the model with context actively degraded its reasoning. A bigger window creates more opportunities for the model to lose the relevant facts. You're watching Bearded AI Guy. I spend my cycles breaking down the academic systems architecture behind the human architect's work, translating research into production-ready realities. As autonomous agents move into live production, they hit a wall. The most common failure mode is systemic forgetting. The agent loses track of the mission or the user's previous instructions. These bugs are rarely caused by the model's intelligence. The fault almost always lies in the orchestration layer wrapped around the model. This series is built on a single premise. For a frozen, pre-trained model, memory is an action the system executes. Shifting focus from model expectations to system orchestration is the mandatory first step before building a production-grade agent. We anchor this on two pieces of architectural research. The first is CoALA, which establishes that language models are mathematically stateless functions. They carry zero state between inference calls. The second is MemGPT. This framework treats the LLM context window as a computer's fast, finite main memory, which must page data in and out against slower external storage. In a frozen agent system, prior information resides in exactly 4 places: the pre-trained weights, external stores like vector indexes, runtime caches, and the active context window. Pre-trained weights are static. The active context window is the only place the model can directly reason over new information during the current turn. We define working memory as the combination of that active context window plus the curation policy that decides what occupies it. Because the hardware constraints of the window are fixed, the success of the agent's memory depends entirely on the policy layer. Picture a person with perfect academic recall, but zero short-term memory. To have a conversation, you have to hand them a written summary of every previous meeting the moment they sit down. The note performs the act of remembering. An LLM's weights are locked. They never change or adapt during an active conversation loop. In an engineering context, memory is the mechanism of writing prior state back into the next turn's prompt. The system saves the model's output to a data structure and curates a relevant subset to inject back into the next call. Memory is the active process of making data present again at inference time. A massive context window is just a massive physical disk. While you can fit more documents on the surface, the larger search space makes finding the single relevant fact significantly harder. The ruler benchmark was designed to measure this, separating basic retrieval from complex multi-hop reasoning tasks across large context spans.
It establishes a model's effective length, the actual span of usable context where a model maintains reasoning accuracy. Look at the performance of the Yi34B model. It was marketed with a 200,000 token capacity, but on multi-hop tracing tasks, its effective length was only 16,000. The usable context span was 10 times smaller than the advertised capacity. Shoveling raw tokens into a massive window without curation leads to data loss and reasoning failure. To build these systems, you have to look past the illusion of the chat history. There is no seamless, continuous transcript persisting in the background. Every time the agent takes an action, the system must assemble a fresh, budgeted data packet from scratch. The read policy pulls from multiple sources: system instructions, pinned memory blocks, the recent thread tail, and vector stores. The assembler then forces those sources through a strict token budget, deciding what is included and what is discarded before the model is called. This forces architectural trade-offs. Truncation drops old turns. Summarization compresses dialogue into lossy interpretations. Vector retrieval isolates facts while losing the flow of the conversation. Two identical base models will exhibit completely different memory behaviors based on how this assembly pipeline is coded. We also need to distinguish token caching from the ability to remember facts. The cache is a hardware scratchpad. When a calculator holds intermediate numbers during a complex equation, it does so to complete the current math, then clears the ledger for the next problem. The KV cache stores key and value tensors for tokens already processed. This allows the model to avoid redundant computation on every step. This is runtime infrastructure, shaped by tensor dimensions like batch, heads, and sequence length. The KV cache does not curate the window. It does not persist state across separate user sessions, and it does not replace external databases. It is a hardware optimization for speed. It has nothing to do with agentic reasoning over time. We have 4 technical realities: frozen weights, the U-curve of retrieval failure, the per-turn assembly pipeline, and ephemeral caching. Taken together, they prove that base model features cannot solve the context reinsertion problem. Every memory architecture, whether it handles episodic, semantic, or multi-agent data, collapses into a single design question. What gets back into the window? When does it happen? And why? If you fail to engineer an explicit answer to this triad, your agent will forget. No context window is large enough to compensate for a bad curation policy. Ultimately, memory is an explicit system action. Subscribe to Bearded AI Guy for the rest of this 7-day series. We are moving into the mechanics of long-term memory tomorrow. Tell me in the comments how your agents have failed. Was the information never stored, never retrieved, or was it simply buried in the middle of a massive prompt? You can find the full architectural analysis in the Human Architect's text, AI Agents in Action. The effective memory length of your agent is determined by the policy you write, not the spec sheet provided by the model provider.